Well, thank you very much, Jonathan, for that welcome, and thank you very much to Laurie and Bernd for inviting me to this very impressive conference. And it's a great pleasure to be here and talk about something that's been concerning me more and more over the last few years, and that's climate change. So this is a graph. It's actually 6 independent graphs of global surface temperature over the last 150 odd years. And you can see that the, if I can get it, it's sort of wiggling around here and flattening off, but it's generally going up. And this, of course, is what's become known as global warming. When we talk about global warming, you hear people say sort of a few degrees warming, and we have to be a bit careful about what level we're talking relative to, and there's some confusion often in the press as to about what's going on. So this, wrong one. This is actually deviation from the 1980 to 2010 average, so the 0 is over here. But you'll usually hear people in the climate change world talk about the difference from what's referred to as pre-industrial. So before we had lots of industry and burning fossil fuels in the economy, and that's the average from 1850 to 1900, and we can see that the global temperature is now about 1 degree warmer than it was then. Which doesn't sound very much, but we'll see actually it's having quite a big effect, and the larger it gets, the worse of an effect it's having. So what I'm going to talk about today is some of the physics and chemistry involved in the factors influencing climate. What evidence is there of climate change, and how can we understand the causes of it? What things might look like in the future, and then thinking how we might do something to address this. So, cut to the chase, we need to decarbonise the economy, stop emitting CO2 into the atmosphere, and looking at ways in which that might be achieved, and the international policy and agreements that are being put into place to try and achieve that. So here's my noddy graphic, sorry about this. That's the sun, that's the earth, and all the energy coming into the climate system is coming from the sun. The amount of energy coming from the inside of the Earth is absolutely minuscule in comparison. So all the energy driving the climate system is coming from the sun. So we know how much energy there is coming in, and we can work out the temperature of the Earth that would be needed to radiate the same amount of energy. So that's an equilibrium. And we can work out that the power in balancing the power out will give temperatures minus 18 degrees Celsius. So you'll be thinking, hang on a minute, she's just said it's easy physics, and her answer's a bit wrong. What, minus 18 Celsius? So what's the problem there? The problem is, of course, that the minus 18 Celsius doesn't refer to the surface of the Earth. And to understand what's happening at the surface, we need to understand what's happening in the atmosphere. So this picture is of the Earth's energy budget. And at the top here, we've got the solar radiation coming in, exactly as in the last picture. And we've got the heat radiation going out. Some of the solar radiation is scattered back to space. But if you balance out everything here on an annual average, and if there's no climate change and everything's in equilibrium, then the same amount of energy is getting absorbed as is getting emitted to space, and that's an equilibrium. But then we see what's happening within the atmosphere, and about half of that energy coming in the top gets absorbed at the surface. And some of it's scattered back to space, as I've already mentioned. About a quarter is absorbed in the atmosphere directly. So the surface is absorbing this solar energy, and so it gets hot. And then it emits heat energy. This is this bit coming here. But what we see is that only 5% of that actually gets directly to space. And 95% of it is absorbed in the atmosphere. Then the atmosphere itself is made of material, it's made of molecules. They can get hot and they can radiate, and they will radiate both upwards and downwards. And so what you've got is more energy coming back into the surface and making it hotter than it would be otherwise. And this is known as the greenhouse effect. It's rather a bad name because greenhouses don't work like that, but never mind, that's what it's called. And so when everything's in balance, you can see that the surface temperature is going to be warmer than the minus 18 degrees that that simple model was suggesting. And so greenhouse gases here are absolutely fundamental in determining the surface temperature of the Earth. These gases here trap the heat and make the surface warmer. So let's think about gases in the atmosphere. As you probably know, about 80% or a bit less is nitrogen, about 21% is oxygen, 1% of argon, and then a small percentage here of carbon dioxide, 0.04%. That's of the dry atmosphere. We've also got some water vapour, which is very, very variable over the globe. So those are the gases in the atmosphere. Which are the greenhouse gases? Now, what happens is that these very common gases, the most common ones, don't have a greenhouse effect at all. So they're just quite happy to let the sunshine come in and the heat go out, and they're not interested in the energy balance. Water vapour is the strongest greenhouse gas, and that's responsible for about 2/3 of the temperature raising that's due to the greenhouse gases. And then we've got carbon dioxide here that's doing the rest. So carbon dioxide is key to keeping the surface warmer, but it's only got this concentration of 0.04%. And you might ask the question, how can only 4 molecules of CO2 in every 10,000 of air possibly have any effect? So this is probably the most scientific plot in my talk, so if you find it a bit threatening, don't worry, I'm not going to carry on in this vein. But it's a spectrum. It's a spectrum of the heat radiation. So you'll be very aware of light having a spectrum going from red to blue in the visible region. This is a spectrum in the infrared region, so we're getting wavelengths, getting longer wavelengths over here. And the red curve here is the radiation spectrum that would leave the Earth if it was at a temperature of 21 degrees Celsius. The spectrum that you can see with the wiggles is a measured spectrum, so that's what's really happening. And what you haven't got a smooth profile like this. What you've got is something very, very wiggly and with big bites out of it. And that is due to the gases in the atmosphere. So you see that water vapour over here is absorbing a lot of the radiation coming at the shorter wavelength end and also at the longer wavelength end. We've got other gases like ozone taking a bit out of here and methane taking a bit out of here. But there's a great big bite out of the middle here by CO2. So it just so happens, perhaps the chemists here will tell me whether it's a so happens or it's designed that way, but anyway, it just so happens that the properties of CO2 molecules, they vibrate in just the right way as to absorb radiation at around, say, 12 to 15 microns wavelength. And that just so happens to be the peak of this spectrum of the radiation that would be leaving the planet were it not there. So it's a sort of double whammy of CO2 being at the peak of the spectrum and having a very strong absorption at those wavelengths, along with the fact that nitrogen and oxygen have no effect at all, that makes carbon dioxide uniquely absorptive and having this greenhouse effect. So, of course, the follow-on from that is that if you increase carbon dioxide in the atmosphere, it'll trap more energy and create even more warming at the surface. So let's see what's happening to carbon dioxide in the atmosphere. I'm going to show you several graphs now. They're all going to show you carbon dioxide concentration as a function of time over different time periods. And here we've got the 0.04% that is the current concentration. And this is hundreds of millions of years ago. And as we heard earlier just today, first primates didn't appear on Earth till a few million years ago. And so by that time, the carbon dioxide concentration is down here at much what it is today. Now, if we get more recent, we have now the 0.04% is right up here. And as we go hundreds of thousands of years, you see it's going up and down, but it's always below about 290 parts per million, or 0.029%. I'll come back to the shape of this plot a bit later. And modern humans, again, as we heard earlier today, didn't appear till about 200,000 years ago. So here's a less exciting plot. This is going up to 10,000 years ago, and it's fairly flat, around 280 parts per million. Carrying on to the last 1,000 years ago, it's fairly flat, and suddenly we get this little whoopsie at the end there. And if we look in more detail, this is measurements at a very clean air station in the middle of the Pacific Ocean on Hawaii. And these measurements are very, very careful, and they're done every year. And you can see there's a little annual cycle, which we can see more clearly in this 5-year. But there's upward trend, and that red there is the same as that red there. So what you can see from this collection of plots is that the CO2 that we've got in the atmosphere now is not anything like has been seen with the life on Earth as we know it. Certainly humans have never been living in an atmosphere with this amount of carbon dioxide. So we now have something like 400 parts per million, whereas before we had 300 parts per million, so it's gone up by 30%. So you think it's a small fraction of the total atmospheric concentration, but in terms of fractional increase, it's huge. And it's going up, it's carrying on going. So back to this. So just to consider what other things very quickly might influence the surface climate. What about the sun? Of course, you might think that if the sun's radiation is changing, that would affect the climate. And we're going back to these hundreds of thousands of years ago. And here's a plot of temperature. And you might say, hang on a minute, I've seen that plot already. You haven't seen that plot already, you've seen the CO2 plot, but you can see they're very, very similar. And the cold periods in here are the ice ages. And what happens here is that the Earth's orbit around the sun is changing on these very long time scales. So every 100,000 years or so, the ellipticity of the orbit changes a bit. And so there'll be periods when there's less solar radiation coming in, and so the climate will get a bit colder. But that sort of energy is not nearly enough to produce these 5 or 7 degree temperature changes. What happens is, if you get the Earth getting cooler, then you get more absorption of CO2 and also methane into reservoirs in the oceans and in the ice. And so there's less greenhouse effect, so it's cooler. And then the other way around, as it gets a little bit warmer when the sun's orbit changes again, a little bit warmer due to the sun, then you get more CO2 as it's released from the stores, more methane, and it gets warmer and warmer, more greenhouse effect, it's warmer and warmer, you get this very sharp increase in temperature. So you've got these ice ages which are initiated by changes in the Earth's orbit, but they're amplified by the CO2 and methane, so it's actually the greenhouse gases that are doing the warming. So can we explain the shape of this graph? You've seen this already. We'll look now at some model simulations. So these models are general circulation models of the climate system. They're exactly the same in terms of their physics and construction as the weather forecasting models that you see that give the weather forecasts for the TV news every day. But we run these models on a larger scale for longer time periods to see what happens in the climate. And in those models, we can simulate various processes. So here's some of the processes that we'll include. The greenhouse gases I've already mentioned. We put in industrial pollution. Now that might be other things like greenhouse gases, but it might also be particulates in the atmosphere that can scatter sunshine to space. Land use, so that will affect the brightness of the surface. If a place gets more bright, more desert, or less forest, if it gets brighter, it will reflect sunshine to space and a cooler planet. We've put the sun. You can put in volcanoes. So if you get a big volcanic eruption, it puts stuff into the atmosphere that will last there for perhaps a couple of years, and that also has a measurable sense of cooling temperature. This is an important one, energy transfer in and out of the oceans. So I've been talking about the atmosphere, but the oceans are a fundamentally important part of the climate system. And then you've got this noise, so you've got all these sort of wiggles. Now, I said model results. And what you've got in here, you see this spaghetti of curves. All of those are different individual model runs. So if you start from a very, very, very slightly different position, your model will go on a different trajectory. So that's why there's so many different spaghettis in there. But you can see that the envelope of these model runs follows the observations, which are shown in black here rather well. So within the spread of the model runs, that it goes round the observations. And that's the plot I've just showed you. If we do the same runs, but we only include natural forcings, which would be the sun and the volcanoes, it doesn't do a bad job over here, but you see here's the observations, the measurements of temperature going up here, and the models just can't do it. So that's another way of understanding that it is the human influence that's producing the global warming. We call it global warming, but it's not the same all over the globe. So this is a map of the difference in temperature between 2012 and 1901, so just over 100 years. And you can see it's not the same everywhere. You've got some places, particularly over land masses, where the temperature increases have been about more than 2 degrees. Some places where it's less, and some interesting places, here we got in the North Atlantic, where it's not changing at all, or possibly even cooling. Now, of course, from a physics perspective, this is very interesting, and the oceanographers are getting very excited about trying to understand why this is, and it's probably related to changes in the deep ocean circulation driven by the climate change. So when we talk about global warming, it's not the same everywhere, and it may be 1 degree across the globe. But if you're living in North Africa and your temperatures are already sort of 40 degrees and you're going up another 2, life becomes even more difficult to carry on in those temperatures. So global warming is not the same everywhere. I've talked about temperature, I've just stuck to temperature, but of course there's other information on what's going on in the climate. One other line of evidence for climate change is the area of the Arctic sea ice in summer. So you'll be very well aware that there's an annual cycle, there's less sea ice in the summer and more in the winter, and you can look and see where the minimum area in the summer, usually in about September, occurs. And you can monitor that. There's 2 examples here. That was in 1979, and you can see the sea ice right the way around here. That's in 2011, and you can see it's a much smaller area. We have to be very careful about not drawing conclusions from just essentially a sample of 1 there. But if we look at the graph of the area, you can see very clearly that the sea ice minimum is, again, it's got wiggles in, it's a noisy system, but it's going down. And people lay bets on the first year when there won't be any sea ice in summer, Arctic sea ice in the summer. An important follow-on from this is that there's a positive feedback effect. So if it gets warmer and we have less sea ice, then we have less reflection of solar radiation back to space, which means more absorption of solar radiation, which means more warming. So this is a positive feedback on the initial warming effect. Other evidence, this is sea level rise. This is a measurement over the last 100 years of what sea level's doing. It's gone up about 20 centimetres here over that period. And that's coming, that's by century. So that's this last century. And this previous centuries is up and down, not very much, but you can see this is a big increase. It's coming from glaciers. So this is a picture of Greenland, and there's a blue line drawn on there, a position of a particular glacier, and that's a photograph of it. And the sea level rise is essentially approximately half due to melting of ice on land, so ice sheets and glaciers. Note that melting sea ice can't change sea level because it's already floating, so it doesn't affect the sea level rise. Also, about half thermal expansion of the oceans. So as the oceans get warmer, they expand. They've only got one way to go, which is up. So that's raising the sea level relative to the land. Now this is a picture, and the focus of this is on weather extremes. I've talked about averages a lot, and global averages and area averages. But of course, when you experience the weather, you're in a particular place, you experience something local. It's not quite the same thing. And what this is a distribution of summer temperatures over the northern hemisphere. So if you've got this distribution, that's the average. Some places are warmer, some places are colder. That's just what you'd expect. But let's see how that changes. We're starting off with, and this is 1950 to 60 average, and we're going to see what happens as, I hope we're going to see what happens as the years move forward. So what you're going to see is 10-year averages moving forward 1 year at a time. We're keeping the colours the same as they were in the original plot. So as time goes on, you can see the distribution moving to the right. This is just global warming. Essentially, the average is going up. But what you also see is that something, say this unit here, it's 3 standard deviations. Originally, that would have been something like 1 in 1,000 places have got that high temperature. But by the time you get to now, that particular temperature is now a 1 in 15 event. So it means that you're going to get more extreme heat waves and actually fewer cold periods under global warming than, and that has impacts on health and business and all sorts of things, agriculture, of course. So summer 2018, which was extraordinarily hot, will just be normal by summer 2050. So looking to the future, we've already discussed that the principal cause of global temperature rise over the 20th century has been greenhouse gases. If we're going to predict what's happening in the future, we've got to predict what's going to happen to the greenhouse gases, and that's actually rather difficult because you've got to predict the economy and what's going to go on in it. So I focused largely on carbon dioxide, but there are other greenhouse gases too that need to be considered. And if we consider where they're coming from, about a quarter is coming from electricity and heat production, about a quarter from agriculture, something like a quarter from industry, and then the rest from transport. And so we have to predict what's going to happen in each of those sectors. And I'll have to whiz through this rather fast. This is primary energy use and where it's coming from. And this is what the state was in 2000, a lot from oil, gas and coal. And these are representative concentration pathways, sorry about the jargon, as by the Intergovernmental Panel on Climate Change scenarios for different ideas of what might happen by 2100. So this one here, which has still got lots of coal and fossil fuels, and this one over here has still got a bit of coal, but a lot more on bioenergy. So there's these different scenarios, and there's ideas of what might happen in the future with these emissions for these different pathways. So you see this green one, which is the 2.61, it goes up a bit and then it comes down and goes to 0 by the end of the century, whereas the blue one, it carries on emitting. That's the emissions, but the concentrations is something else because carbon dioxide is very, very long-lived. Once it's up in the atmosphere, it'll stay there 200 years odd. So you put it up there, it stays there. And so the concentrations are doing this. So even the one where you're stopping emitting, it hasn't got back to where it started. So I've got to go through this rather quickly. Have a look at this if you get a chance, globalcalculator.org. It's great fun. You can choose all sorts of things to do with how you're going to travel, what you're going to eat, all sorts of different things, and you get different temperature rises and different energy demands, and the graphs will do this. It's great fun. Have a go at that. Future temperature, this is just the 2.6 and the 8.5 scenarios. So we've got temperatures going up by around 4 degrees for the worst one, and more than 1 degree for the 2.6 by 2100. And again, of course, it's not the same all over the world. This is the 2.6 scenario, that's the 8.5 scenario. This is temperature, and this is rainfall, precipitation. Some things are not very certain. We're very certain about the warming. Rainfall's more difficult, but it's definitely seems to be definitely drying over the Mediterranean and increasing in the tropics. So the wet's getting wetter and the dry's getting drier. This is sea level rise. You can see it's gone up by 1 metre by the end of the century. And there's all sorts of other things that really impact people's lives. And of course, these are very difficult to predict. But by using these climate models and looking at sort of economic scenarios and things, we can suggest these sorts of numbers. These are big numbers. You can see the sort of effect on people. And I'm not going to read all of these out. You might say, hang on a minute, if there's 12 billion people getting exposed to heat waves every year, that's more than the world population. That's because some people get it more than once a year. So more heat waves, and some people getting less water when they need it, some people getting flooded when they don't need it. So it's that's the message. You might have got it already. So it was an amazing achievement when the United Nations agreement in Paris in 2015, there was a unanimous agreement to do something about it. You can't imagine what a wonderful achievement that was. The previous big conference like that had been in Copenhagen in 2009, and as sort of environmental scientists, we were just hoping something would be agreed. Absolutely nothing was agreed. It was just such a disappointment. So when it came to this meeting in Paris, we were thinking, please agree something, please. And not only did they agree something, it was a unanimous agreement. And they specifically said that they would try to keep global temperature rise to well below 2 degrees above pre-industrial and to try and keep it to 1.5 degrees. This is a huge international achievement to have got to that situation. So we must start from a position that that's a good. Of course, the not so good is, are they actually doing what they said they're going to do? And this is what it means. So that's the temperature rise up till 2008. The blue is what would happen if we carry on going. By 2030, we'd be up. Sorry, this is CO2 emissions. I beg your pardon. That's what's happened up to now. That's what will happen in the future. The pink curve here is what would happen if all the countries delivered on the promises that they made in Paris. So the Paris Agreement was amazingly good, but it's just nothing like enough. If all the countries did what they said they would do, even if that, then it's not really having a huge effect here. And what we need to get to 2 degrees is CO2 emissions to do this, and for 1.5 degrees for them to do that. So this is what's referred to as an emissions gap. Gap between what we need and what we got. And I think, yes, so if you think you're going to decide on a temperature rise that you want or you don't want to exceed, so it could be 2 degrees, it could be 1.5 degrees, you might even decide, oh, I don't mind if it could be 4 degrees, or choose a temperature and you think that's okay. Whatever temperature you choose, at some point in the future, you've got to stop emitting CO2, because if you don't stop, the temperature will carry on rising. So, even if you want 4 degrees, you've got to make some decisions about stopping CO2 emissions. It'll be later rather than sooner, but I think the sooner rather than later is a better aim. So there's ideas about how many years of current emissions we've got left to avoid various temperature rises. So if you want to have a 50% chance of not exceeding 2 degrees, we run out of that in 28 years. You get the picture. The more we emit now, the sooner we need to stop so that we don't exceed one of those thresholds. This is from a report from the Intergovernmental Panel on Climate Change last autumn, in which they looked at global pathways to try and limit warming to 1.5 degrees. So again, this is emissions as a function of time. There's lots and lots of curves on here. These are all different pathways with different scenarios that you can see. But in order to get to less than 1.5 degrees, if you peak sooner, this is the green ones, you don't get, well, you get to a sort of net zero by 2050, but you don't have such a negative value at the end there. With the grey ones, if you leave it a bit longer, you get to net zero about the same time, but then you've got to have these negative emissions by the end of the century. So what do I mean by net zero, and what do I mean by negative emissions? Net zero is acknowledging that it's going to be very, very difficult to stop emitting CO2 into the atmosphere completely and other greenhouse gases. So what we've got to do is not only stop emitting, we can emit as little as we can, but we've also got to suck some of it back out again. So at the end here, this negative here means we've got to be sucking more out of the atmosphere than we're putting in. That's a technological challenge. So a delay in the peak means greater carbon capture is needed later. So I just thought I'd show you a little bit about emissions by country. So these graphs aren't very clear, but again, another lovely website if you want to play with this one. It's got all the data for all the countries' emissions over time, and you can compare countries and compare dates and different greenhouse gases and things. So over here I've got China, India and the USA. And you can see that USA has been going up. It's sort of flattened off a bit recently. China, of course, has gone right up, but then it's flattening off. So it's it's doing a lot of renewables now, China. India, this is gradually rising, of course. And if you look at the per capita emissions, so the amount per person, of course, the amount from India is much less. So we have to try and think about equitability and fairness of all this. On the right, I've got some other countries. The green one is Germany, so they've been on the decline here. Similarly, UK has been declining quite a lot over the last 10 years, and France is similar. Sweden, of course, is a lovely, clean country, doesn't emit much at all. This is a slightly shocking one, is Australia, which is just carrying on going up. So if we look at the difference in per capita emissions between the last period over here, you can see the developing world is increasing, which is, you can say is perfectly reasonable. These people have a lower standard of living than us, and they weren't responsible, like us, for emitting the CO2 in the first place. So if they're increasing, that may be fairer. The question is how to help them get through it to a modern society, a higher standard of living, without going through all the dirty sort of stuff that we've done. And countries in the north up here largely decreasing, which is good. So, here's the message. Action on climate change. This is what you can do in your lives to try and make a difference. First of all, save energy. You can insulate your homes. In the UK, if everybody insulated their homes properly, that would do half of what we need for getting to our carbon targets. It's just saving on energy. If you've got the option to choose renewable energy, do that. So choose companies to buy your electricity from that are green sourcing. Create less waste, all kinds of waste, food waste, plastic waste, just throw away less. That will save on energy and the environment. If you get a chance to walk or bike instead of driving your car, you can, emit less CO2 that way. A less meat diet, particularly less beef and lamb. They're very, very high intense agriculture, emits a lot of greenhouse gases into the atmosphere. And importantly, of course, this is all the things that you can do personally, but the politicians have got to make the legislation to help us all go in the right direction. So lobby your member of parliament and make sure you vote in the right way so that we get the politicians to do the right thing. If you'd like to look at the Grantham Institute website, there's 9 things you can do about climate change, which is more details of this sort of thing. And I'll stop there. Thank you.